So I'm delighted to hand over now to Margrethe Broby, who can take us through the dashboard from Okea's view.
Okea is a company specializing in late life fields on the Norwegian continental shelf. And late life fields means that you often get what you have. Installing everything new is often not an option. And when it comes to chemical monitoring, that has been my challenge for the last year. I'm a production chemist, and one of my tasks is to ensure that we dose the right chemical at the right place at all times when we need it. And that has been a challenge up until now. Now you can click. So this chemical dashboard, it came as an idea because we needed to improve the chemical dosage monitoring at Brage. Brage was previously operated by Wintershall, and in the transition to Okea, we lost a lot of the features that they had already been developing. So from November 2022, we were kind of left with no trends at all. So how did we know what we were dosing of chemicals? Well, the truth is we actually almost didn't know. We have no flow meters, and some of the tank level measurements are not always stable. And now you can click one more. What is really important when it comes to chemicals is that dosages matter. So we needed to find a system that could calculate the dosage, not only the rate of the chemical, but the dosage of it, so that we could make sure that the chemical performance would be ideal. I've just put in a few pictures here, and this is linked to the performance of one of our chemicals. This is samples taken from bottom to top from one unit operation at our platform. And ideally, it should be like the picture down to the right. You should have clear water at the bottom, and you should have no interface, and you should have a clear oil phase on top. But if you overdose the separation chemicals, it can end up looking as the top picture, where you have sludge, 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 and a little bit of sludgy oil on the top. And of course, that gives us poor performance of the separation process. It increases our emissions to sea. And it's really not how we would like to run the process. And the reason for us coming into this situation can be that we are dosing too much or too little chemical. So we have to know what we're dosing. But it can also be that the pump has broken down so that we think that we dose chemical, but we do not do it. Or the injection valve has an issue and suddenly doesn't inject what we think it injects. So there can be many sources of mistakes here, and it's important for us to be able to differentiate what is that we're not dosing the recommended dosage, and what is we have the right dosage settings, but we are still not obtaining this dosage. So that was where I started last year. So we can only access the actual injection rates by in field by using a manual calibration cylinder. So that is important to know. So you have to go to the pump and you have to let the flow into a graduated cylinder, and you have to note down the time it takes. That's your only real calibration you have. And then we have a tank level measurements based on density. And of course, as with everything here, since it's a dosage, if your water rate or your oil rate changes, you should also go and change your chemical injection rate. So now you can go to the next one. So the previous process where we started was that we built a basic spreadsheet, and that gave us a theoretical consumption where we averaged over a quite long time to be able to find an averaged consumption, and you could calculate the concentration of each chemical based on the tank level measurement and exported flow. This was done by manually loading data from Pt1, which is our data source, on a weekly basis. And this could only be done onshore because the spreadsheet was big and heavy and required you to have the right add-ins in your spreadsheet file. It was slow, and it was really inaccessible for the offshore crew. So we had to tell them that currently you are dosing this. That is wrong. You have to change it to this. And it was all very difficult to optimize from. So we thought we have to be able to do this in a better way. So what we do now with the help of Eigen is that we still calculate the flow rate based on the tank level, because that is really the only measurement we have. But now this new process identifies which tank is flowing, because we usually have two tanks, and often one is filled while the other one is flowing. So you have to be able to differentiate between those two. And then you pair these rates with real-time measurements of flow so that you can calculate a real-time dosage. And then you can calculate a deviation from, okay, we have a recommendation, which is this concentration. Given this flow rate of oil and water, it should mean that you should dose this rate of chemical. And then we can check what are we actually delivering from the tank. And at all times, you can see a deviation. And we have these small traffic lights showing whether you have to go out and take action or whether it's okay to leave it as it is for now. So you can click one more. Yeah, so there are several benefits of this. One of them is that the dosage recommendations are updated with a response time of 2 to 4 hours. You're no longer dependent on one person's manual work on a weekly basis. So you have, in case you close a well or you open a well or there are big changes happening, you can see the same the changes within a reasonable time. Also, and maybe as important, the data are gathered in one place and is now accessible for both the onshore people, but as also for the offshore operators. So now the operator can either print the screen or just take a photo with the EX phone of what should the dosage be, and then go out and check, do we have the correct dosages given how the process is today? So that is really, really beneficial for the operators. It also allows us to identify if there are pumps or injection valves that have irregular performance, because we can now see, okay, we have the right configuration, but we still don't get the right rate. Why don't we do that? And that has helped us identifying process disturbances at a much earlier state. Of course, it also prevents overdosing of chemical if used correctly. You're still dependent that someone goes out and calibrates it correctly. But there's a cost-saving potential here, and there's a huge potential for improving performance and securing ideal performance. And one feature we're also looking into with the Murray is to trend consumption. So because you can track a tank fill, you can also note how much did you fill at all times, because our chemical tanks are smaller than the transport tanks, but then you can make an accumulated consumption, and that can ease the planning of the chemical logistics, which is right now a very manual process as well. So we are very happy working with Eigen, and we look forward to continuing the improvement of this chemical dashboard.
We can actually pull these screens up, Marguerite, if you like.
Yes.
So oops, come back. So this is just a summary of the tanks. So here we can see which ones we believe are flowing at any time, and we compare the estimated flow, our last trusted flow, and the average flow. And this lets us see when it's stable. So if the average flow equals the estimated flow, then everything is stable. If we see one where there's a difference, at the moment they all seem to be stable, then it means there's been some change, and maybe the average is moving, and we're waiting to see if we trust it again.
Can I just have a comment here?
Yeah.
Because right now we do have an issue with our flocculant. And one of the reasons why we know we have an issue with the flocculant is that currently it says 6.6 liters, I think, on the dashboard here.
Yeah.
While that's not what it says on, because it's on this particular valve, we actually have a flow measurement on the valve. There's a display on it, and that says 2.5 liter. So we know that there is something ongoing with that flocculant, and if we hadn't had a calculation here that we can trust, and you can also see from the consumption trend that it's bigger than what is currently displayed on the valve. So this has helped us identify that now we need some maintenance here.
Yeah, that's interesting. So funnily enough, I was looking at this tank earlier because this is probably the most unstable of all the tanks. So if I put on what we believe is the estimated flow, I'll make it blue, and we can put it, maybe that's harder to see and make it a different, let's make it green. Yeah, we can see here that we have a period of time before we are sure the tank's flowing. That's because we have to take a 10-hour window before we can say for certain that a condition is true, because of the instability. So when the tank has not been flowing and then starts to flow, we, especially after a fill, it takes 10 hours before that massive spike has worked through. But anyway, it comes online and it's fairly stable, but then we can definitely see we get an increase in rate. And you see here after the stability period, we say, yeah, we're definitely happy. There's a change in rate and our flow rate, calculated output, has gone up. If I add on then the average flow to this trend, what we'll see, there it is. And this one, let's make that, what's a good color here? Light blue. We'll put it on the same axis there. There you can see the average flow. It moves around a lot more. You could say maybe we should have trusted it earlier in this case, and that's we can look at maybe some more logic in that, but then it falls pretty quickly to this stable period, and then it responds quite quickly. And you can see the points where we start believing it as the trusted flow. Then for this period, we take the average, but then we wait a bit. There's a big instability and we pause before we are happy again. And it's moving like a sine wave at the moment with the instability, but the overall, the trusted flow is staying pretty constant. So this is a great example of the challenges we've had. It's about the most unstable tank of the lot of them. But this is the dashboard then here that's in use. It loads pretty quick. That's one of the improvements, I think, because there's a bit less going on at runtime. The calculations are now done behind the scenes, whereas before a lot of them were done at runtime. But the lines are a bit clearer, I think, than before. And everything's interactive. It's all trendable. So anything can be clicked and bring up a history of the value. And like before, you can change the time period for things. So the operators can quickly check if they're happy with things.
Mary, is it possible that you show the details of what are the calculations done in the calculation engine so people appreciate how they're done?
We definitely will do that. And Denise will be doing that in session 4. Yeah, she's going to go into detail on that. That's right. Because some of them are straightforward. It's just a chemical divided by one flow, but certainly the downhole one becomes quite complex. That's quite a big calculation to do. So, yep, Denise will be showing that.
And I have one question for Margaret, if you don't mind. So,
yeah, please.
Could you go into details about why overdosing messes up with the process?
Well, that depends on where you are in the process, but many of these chemicals, especially the flocculant and the emulsion breaker, will have an optimum window because they, like the emulsion breaker, it should target the interface between oil and water. If you overdose it, you can drag oil down to the water, and if you underdose it, you will not be able to break the emulsion. Okay. So most of these chemicals, you will have a vendor out with you or as a chemical supplier, and you will test and you will find a dosage range. And that is actually what you see as the green band here. That is the recommended dosage we should try to stay within. So we would like that blue line. If you look at the corrosion inhibitor, which is the one to the right, there we have the blue line, which is the calculated rate within the green band, which is good. That's where we would like to be. For the emulsion breaker, we're just below. For the flocculant, well, we have some, that one is our little problem baby. And for vaccine inhibitor, we're currently a bit high, but we've just turned it down. So there is a performance component to all chemicals. And these are linked to both what you would like to achieve from a chemical, but also, of course, the cost of it. you would some of these chemicals would cost maybe £10 a liter. So if you dose way too much, you're just pouring money out of your plant. But at the same time, also they have an environmental impact, so it's important to use as little as required.
Okay, thank you.
Yeah, excellent. And I guess some of the rates are quite high, 20 liters an hour, and others are very, very low.
Yes,
So,
it all depends
yeah.
on what they are targeting and how they work.
Yeah.
Can I just mention one thing more on the chemical dosage?
Yeah.
If you just scroll down a bit, what we also really, really like is that we can couple this to the lab data. So we have lab technicians offshore that take sample and measure, for example, what the oil content in the water that we discharge, and also the water content in the oil that we export. And we have KPIs for these. And here we can also pull those data into the dashboard. So you can actually trend the effect of the chemical injections together with your lab measurements. And that has not been possible for us previously. So that has also been really, really good for us, instead of having to take out a manual report from our database and then import it into an Excel sheet.
Yeah. Great point. So was this the right trend? This is the Mekong.
Yes, so this is the Mekong. So this is just what did we discharge yesterday. But when we evaluate if we have the right dosage of the separation chemicals, we would also look at this. And as you could see here, we have in the period where we had really unstable emulsion breaker flow, and you can kind of look, if you just look up here, you can see that the emulsion breaker was unstable, and there you also had the blue column rising up. So it really affects, here you can see the direct effect on performance from the curves above. So that is kind of one of the thoughts, that you could couple what is happening and measured in the lab, because that is also offline measurements, with how the two chemicals above is behaving.
I see. And so that's part of the logic of where they are on the page as well, that you can actually just look.
So one of the things I do every morning is that I look at this middle column, and that tells me a lot.
Yes.
So that is also why improving the flocculant would also help us improve better understanding of what is affecting what. Because it's not really 100% clear, if you turn this up a little bit, then you have this effect, but you will, being able to trend it, you can definitely see some patterns.
Right. And do you have it on a screen? Because I know we actually designed it to fit.
Yes, we have it on a screen. We have it on a screen onshore. So I turn around and look at it all the time. But they also have pulled it up offshore, and now they're starting using it more and more. So this dashboard is probably most for me and for the discipline responsible, while the more detailed versions and where the recommendations are just listed is what the operators are using. And we also encourage them to come with wishes of if there are trends and dashboards they would like us to expand with, that eases their workflow. So one thing I've been discussing with Denise is we dose a biocide once a week, and they would like to know, how do we know that we have dosed enough liters? Can we build a dashboard for that, so that they can actually have a look at it while it's happening live? So maybe we'll look into that later on.
Yes. Okay. So tank flows is not actually something we're going to look at today in terms of the algorithms, but yes, it's one of the things we're calculating is every time there's a tank fill, because we can tell. I think one of these trends actually has it. There we are. We can see every time there's a tank fill and work out when it started, when it finished, and what the change in level was. And that was what you mentioned earlier. As a second check, then we could look at this over a longer period of time.
Yes, and you can also more easily plan what are we actually using of chemicals, so that we don't have to run out of or or order too much. So we order the correct amounts. Yeah.
Yep. That's brilliant. Thank you very much, Marguerite. That was fascinating. I didn't even know all of that, and I've been working on it for a while. So thank you. Really insightful.